Now substituting this partial derivative, which is 1 back here, we get that the partial derivative of the activation is equal to the derivative of the activation with respect to the weighted input. Now backtracking and substituting this partial derivative in this piecewise function, get that this is equal to the derivative of the activation in neuron V when j is equal to V and 0 otherwise. And going back up the chain, we see that this expression in here, we get a 0 term when the summation index is not equal to V, and we get a non-zero term when it is equal to V. And this eliminates the summation, and we're left with the weight as j, which we substitute with V going to I in layer L, multiplied by the partial derivative of the activation in neuron V of layer L minus 1. And this partial derivative, as we saw, was equal to the derivative of the activation with respect to the weighted input. So we can write this as, now circling back to our outermost derivative, we have that the partial derivative of the cost function with respect to the bias for neuron V in layer L minus 1 is equal to the sum as I goes from 1 to n of the partial derivative of the cost function with respect to the activation in neuron I in the output layer multiplied by the derivative of this activation multiplied by this partial derivative, which we saw is this expression right here. So we can substitute that back in here and get. That concludes the partial derivative of C for some bias in layer L minus 1. Let's now summarize our results. So now we have generic expressions for the partial derivative of the cost function with respect to biases in the output layer, layer L minus 1, and I've just added the partial derivative in layer L minus 2 just for more clarity. Now when we had a similar setup for weight derivatives, what we did was we looked for derivative terms which were reappearing as you backtracked from layer to layer. We defined a variable which allowed us to store these derivative terms that were reappearing and then reuse them as you go to a previous layer. So for the weight derivatives, the delta term was defined by this piecewise function. You had the delta term for some neuron j in some arbitrary layer L, and this was equal to this expression when the layer index L was equal to capital L, which is the output layer. And then for any other layer where the layer index is between 1 and L minus 1, that is not the input layer nor the output layer, we got this expression. And this shows that in order to compute the delta term for this neuron, you need to know all the delta terms for the neurons in the layer ahead of layer L. So these were the delta terms we defined for the weight derivatives, and it just so happens that we can reuse them for the bias derivatives. And in fact, we can reuse them without any adjustment whatsoever. So if we were to consider the delta term for neuron V in the output layer, we'd have this expression only where we substitute V for J, which is equal to this expression right here. This is delta V in the output layer. So we can use this delta term to compute the partial derivative of the cost function with respect to a bias term in the output layer. This will just be delta V L. And we see that this product follows the same structure. And in fact, this product is given by delta I capital L. So if we substitute that in, we get that we would get this expression right here. And if we examine this expression, we see that this expression can be obtained from our delta formula. So in fact, if we consider the delta of neuron V in layer capital L minus 1, applying the formula, we get the sum as I goes from 1 to n of delta I of layer index L minus 1 plus 1, because we add 1 to the layer index here, which just becomes the output layer multiplied by a weight going from neuron V to I in the output layer as we're adding 1 to the layer index multiplied by the activation of neuron V in layer L minus 1 with respect to the weighted input. And these expressions are the same. which means the partial derivative of the cost function with respect to a bias term in layer L minus 1 is given by delta V L minus 1. And just to reaffirm this pattern, we can do the same thing for layer L minus 2. So I'll just keep the delta formula on the side as an aid. Now, as for this expression, we can substitute for delta I here, and we obtain, and this should be layer L minus 2. Now, just as with the weight derivatives, when we were computing the partial derivative of C with respect to some weight going to layer L minus 2, and we were dealing with a nested sum, we could flip the summations in order to set up a substitution by some new delta term. So that's what we're going to do here as well. So we're going to flip such that the summation with index variable j becomes the outermost sum. Now, looking at the formula, we see that this expression from our delta term formula is given by delta j in layer L minus 1. Applying this formula with index j for neuron and layer index L minus 1, you would get this expression. So if we substitute that in, we get that the sum as j goes from 1 to n of delta j L minus 1 multiplied by the rest of the expression. Now, if we examine this expression and we go back to our delta term formula, we see that if we set the delta term for neuron V in layer L minus 2 and apply the formula using j as the summation variable, we get the sum as j goes from 1 to n of the delta term in layer j. Add 1 to the index, we get L minus 1 multiplied by the weight going from neuron V to j, and again add 1 to the layer index, so we get layer L minus 1 multiplied by the derivative of the activation in neuron V in layer L minus 2. And this summation is equal to this summation right here. So we can state that the partial derivative of the cost function with respect to some bias value in layer L minus 2 is equal to delta V L minus 2. And if we follow this pattern, backtracking from each derivative, we can state that partial derivative of the cost function with respect to any bias term in some neuron V in an arbitrary layer L is equal to the delta term of neuron V in layer L. And so now we have an overall formula for the partial derivative of C with respect to any bias parameter in our network. And just as we stated before, if we have computed all the delta terms across each layer, then we have the means to compute any weight derivative, and now we see as well any bias derivative. And in order to compute these delta derivatives in bulk, as opposed to computing them one by one, we'll resort to using matrix vector notation. And that will be coming up next.